May I ask who the NPTL support is?
Good morning, ma'am. Myself, Bharat from NPTL office.
Hi, nice meeting you.
Hi.
Is there anyone in the waiting room?
No, madam.
Okay. We'll just wait for a couple of minutes. Maybe someone will join. Hey, good morning. So I believe we have one person in the room, Dinesh. Dinesh, are you there? Do you have any questions? You can also type it in the chat room. Hey, good morning. Do you have any questions, Dinesh?
Yes, ma'am. Yes, ma'am. Are you
Do you
audible,
have any
ma'am?
questions? You can also type it in the chat room. Yes, there's a bit of an echo in the background, but I can hear you. If you can, you can ask your question and we'll try to answer it here. So we hope that the uh starting to share my screen. We hope that the videos are quite informative, especially the ultrasound ones with Professor Himanshu and I. So if you have any questions, you can also type it in the chat room, Dinesh. Otherwise, we will go over the questions, provide answers to the questions that were in the discussion forum. Okay. So Dinesh asked the question, explain the receiver side and processing side of an imaging system. Okay, so this could be in one of the lectures that Professor Himanshu had given. So I will try to, Professor Himanshu is unable to join us at present, but I'll try to give an overview of that part of the lectures. And Manu, if Manu here is a TA, and he can jump in anytime if he has any additional points to discuss. Okay, so hope you can see my screen here. So in terms of the receiving side to post-processing side in ultrasound imaging system. So basically first, in an imaging system, we would typically have our transducer here, right? Which is a piezoelectric element. Let's say that it is a array of elements right here. So this is an array of piezoelectric elements. Piezoelectric elements. And we've already learned that piezoelectricity, these piezoelectric elements convert mechanical energy to electrical energy and vice versa. It has a principle of reciprocity. Just 1 second, my iPad. Okay, I'll have to rejoin. Reshare my screen. Okay, there we go. Okay, so of course, we have the transmitting side, right? Okay, and then you have your material of interest. In biomedical ultrasound, we talk about tissues, right? The ultrasound interacts with the structures in the tissue, then you can get backscattering and reflections from larger structures. Then the sound will go back, okay? Now I'm only drawing one trajectory here, but actually what is happening is you send ultrasound signals and eventually the tissues can scatter in multiple directions. So all of the elements will receive the the echoes getting from the tissues, okay? Now, what is going to happen here is that, I guess, depending on whether you are providing some apodization So if you remember that in one of the lectures, apodization is when you're giving weights to the elements, okay? So for instance, if you want to focus some more, you can give weights, you can even give time delays, right? Usually one can decide that all of the elements will have equal sensitivity to the backscattered signals from the tissues. Okay, so you can have some apodization happening here. So then all of this is done electronically, right? So after, of course, this is being controlled by your system right here. You have some data acquisition system here. You will have some, TGC, time gain compensation. Okay, I remember in one of the lectures, Professor Himanshu gave a nice schematic of all the different parts that are being incorporated in the ultrasound system in terms of the post-processing side. So you'll have some, beam forming as part of it as well. Beam forming, log compression. Okay. Right. So let me just organize this in terms of actually what is in more detail, what is happening. Okay. So the data that you receive from your transducer will be in the form of radio frequency data. Okay, or your RF data. Radio frequency is because the ultrasound frequencies are in the radio wave range. Okay, so RF data is being collected. Okay, it will look something like this, high frequency data. And then it is, you calculate the envelope of that using some sort of function called the Hilbert transform. Okay, and this is we call the envelope. Okay, we use something called Hilbert transform to get the envelope of this data. And when you're seeing a grayscale ultrasound image, a conventional brightness mode ultrasound image, you're usually plotting the envelope, but in logarithmic scale. So there would be some compression happening here, just so that you can see even the small amplitude signals. If you log compress it, then the smaller amplitude signals will get more visible. And in ultrasound, that's useful to get to visualize the backscatter from even the smallest structures. So you do log compression. And post-processing on the receiver side, you can have time gain compensation, which I mentioned earlier. Compensation. In your data acquisition, you have beam forming, or it depends on the sequence you want to do, right? So you can have beam forming even from radio frequency data happening here. Forming, this is your time gain compensation right here. Am I missing anything, Manu? Because afterwards, it's the display.
Yes.
Right?
Yes.
Afterwards is your display. And so what I'm showing you here is for typical, your conventional B mode ultrasound. And it's usually plotted in grayscale. Okay. Display in grayscale. And if you log compress, it will be in decibel, in dB scale. Okay, and then the sonographer, the one who handles the ultrasound system, has the capability to look into the range of decibels, right? Range of decibels that the sonographer wants to view. If they want to view more smaller structures, then you would increase we call that dynamic range. Okay. So this is actually important. Like for instance, if you have organs that are very close to tissues with really high echogenicity. So echogenicity, we had talked about in one of the lectures that it's how bright or how much the tissue structure is able to reflect or echo back the signal, ultrasound signal. So there are really high echogenic structures in the body. Like for instance, if you have a bone tissue interface, that interface, because there's such a huge difference between the acoustic impedance, you get a bright echo. So if you have a really bright echo and your display is in decibel scale, sometimes the bright echo will be too bright for you to see any of the lower, um, backscattering type structures. So then the sonographer would adjust the range of dB scales. Usually 40 dB display is there in the scanners, or even 60 dB, 60 dB going all the way down to be able to view the tissues that are less scattering. So I hope this answers your question, Dinesh. These are the steps for how you post-process the ultrasound RF data after receiving them. Okay. Great. You have any other questions? Okay. So what we're going to do now is we have seen some questions from the discussion forum, right? And we can go over each of them. Okay. So Jinesh has another question. Is it possible to implement in hardware? Okay. So, whoops. So basically, implementing all of these post-processing steps in hardware. These are all signal processing, image processing algorithms. Maybe Manu can shed some light on an example of how you can implement any one of these steps on hardware, if it exists.
Okay, let's say we want to detect the envelope. That's one simple step. So you might have, I mean, I don't know if this is how exactly it's being done, but still, if you're from an electrical or electronics background, you learned about peak detection circuits using diodes and capacitors. So that's one way. If you have like a varying signal, you can detect the peak. So that's one way how kind of peak of a waveform can be detected, and that's in a way what Hilbert transform also does. But it's more like, actually it's more like a DSP processor. So you'll have a digital signal processing board which will be doing all this compression, transforming, and everything. But if you want to kind of completely do it in hardware, that's also possible using these peak detection circuits. I hope that is that. So eventually, to answer your question, yes, everything is done on hardware, and multiple ways are there. And the most commonly used method is using this DSP cores, which are kind of high performance ICs, which can do all these computational tasks in hardware. So basically, they are like ASICs kind of chips.
Thanks, Manu. There is one other way, like for instance, time delays, right? I mean, the reason why these arrays are quite useful for imaging in the clinic is because they're fairly versatile. You can focus them at any depth. You can beamform any way you like. But if you want to hard code or basically ensure a fixed time delay, that can also be done with lenses, right? And so I believe there are some deformable lenses also that you can adjust to be able to provide some time delay into your signals. But at present, that is not commercially being used just because it's just much more simpler with signal processing methods to provide electronic time delays into your RF signals from each of these piezoelectric elements. So Manu, can you think of an example where you can use a deformable lens to adjust the time delays of your RF data?
I mean, I know that there are some temperature-based lenses which kind of property changes based on the temperature and everything. So you kind of have heating pads behind, you change the temperature, which will change the aperture of the lens, which will kind of with which you can control where you're focusing. But I don't think those are being used in
Yeah.
commercial systems.
Yeah, so many of those are still in the research stages. Just because, ultrasound megahertz range, you're talking about microseconds waves, and which means that the delays that you put will be on order of microseconds. And if to implement that in hardware, you really need fine precision and smoothness of whatever lens you have to be able to dial in a specific time delay. But I don't think that's being used. I've never heard of it being used in commercial systems at present.
Also, I think it's a lot more easier to control electronic time delay that is given to individual element than to kind of do that part in hardware.
Yes, yes. Okay, hope that answers your question, Dinesh. Any other questions you have? Okay, so we'll now go over the different questions students had in the discussion forum. One of them was regarding the need for isoechoic mediums. Okay, and if there is no backscatter from those mediums. So basically, isoechoic, this term, means that, okay, let's say this is your tissue, and then you have some sort of structure inside the tissue. Let's say it's a tumor, right? Isoechoic means that the backscatter or the grayscale level that you're viewing from your beam mode ultrasound image, it's gonna be the same. So let's say I'll just say grayscale level 1, okay, and this is grayscale level 2. This is a background surrounding tissue, okay. Isoechoic just means that the grayscale level of one of the inclusion or the tumor is equal to the second one. Fairly close, not exactly equal, but fairly close. So this is isoechoic, okay? It does not mean that there is no backscatter from the mediums. It just means they have equal backscatter, okay? If you see something that has no backscatter, it just means that that tissue, the backscatter is in the level of the lowest limit detection of your system. So basically in a B mode image that is mostly black. Okay, but one can adjust their dynamic range also, which I described earlier. Like for instance, let's say that I talked about this dynamic range here. Let's say the highest dB, the 40 dB part, is actually the brightest signal, right? And then below that is like 0 dB. okay, the lowest signal that you can detect. But there could be some other structures that are even lower than that in terms of the backscatter. So then it will appear in your image that there's no backscatter, mostly black. But if you increase the dynamic range to like 60 dB, then you may be able to see some gray pixels that'll come up, indicating that there is some tissue there. All right. Of course, for ultrasound, the media that has very, very low backscatter is something like blood, right? So when I talk about low backscatter, you'll have blood in there because it's mostly fluid. I guess, you know, your urine is almost just there's nothing, not much scatters in the urine, just water and some other nutrients. So then maybe there's if you're going to image the bladder, for instance, there'll be no backscatter in that part. So the bladder, inside the bladder, okay, bladder urine, that will have appear just black in an ultrasound image. Okay, so these ones are called hypoechoic regions. Okay, another one is if there's some fluid buildup in your tissue, they are called cysts, right? So those have also really low backscatter, so they're considered hypoechoic. And this is always relative to the surrounding background tissue. Okay, and the background tissue would be more healthy, normal background. Okay. And so you have hypoechoic, we have isoechoic, and then we have the other extreme, which is hyperechoic. So if you have structures with interfaces that have large acoustic impedance mismatch, then you can get a really bright echo relative to the background on the interface. So like bone, for instance, you can have a lot of buildup of some other proteins, fibrous proteins. So tumors can sometimes appear hyperechoic. Okay. So, my tumor right here. Tumors, just because tumors typically you have more cells that are growing uncontrollably, right? So they can appear hypoechoic. But at times, tumors can also appear isoechoic. So in grayscale, it might be hard to detect any diseased tissue or tumors. So there are other imaging modalities, ultrasound based, that can help you determine whether there's a tumor or healthy, normal tissue around that area. Okay. So another question was explaining M-mode imaging. All right. Okay. So what is M-mode imaging? So the M in M-mode stands for motion imaging. Okay. What is typically done here is that, let's say, okay, if this was your image of a heart, for instance, I'll just draw a heart like this. Okay, of course, the heart has 4 chambers, your atria and your ventricles, like this, right? Typically, when you see an ultrasound image like this, the display is such that the transducer is always coming from the top, and the transducer is looking down at the heart, okay, in this direction. So actually, typically what happens here for this type of heart imaging or cardiac imaging, the transducer would not be from the top of the heart, because you have your bone here, and we know from previous lectures that sound doesn't propagate well through bone because of the high attenuation there. So then usually you would put the transducer under the ribs, so below your heart. Okay, so actually the way I should draw this is, I'm not sure if I'm able to rotate. I can move it around, but nope. Okay, so what you will actually see in a cardiac image, heart image, there's actually a term for heart imaging. It's called echocardiography. In the hospitals, if someone gets an echo, right, typically assumes that that echo is about the heart. Okay, so echocardiography, not to be confused with ECG, which is electrocardiogram. It's not really ultrasound related, but it's a measurements of the electrical differences in your body. So not ECG. Okay. So if the transducer is actually going imaging from the bottom of your ribs, the heart will, the first thing that the transducer, that the ultrasound will see is the bottom of the heart. Okay, so then it will look like this. The heart will look upside down. So then you'll have your ventricles here, and then your atria right here. Okay. So then in M mode imaging, M mode is typically used to image motion or detect motion, right? And it is usually used for echocardiography as well. So echocardiography also involves B mode imaging, M mode imaging. You can have Doppler ultrasound in there also. It's just a general term for imaging the heart. So what usually happens is you get, your transducer will have multiple elements. Oh, let me just draw it as something like that. Okay, multiple piezoelectric elements. And then, of course, the sound will be going in this direction. And of course, you see the image because it's coming back. So in M mode imaging, what the ultrasound system will do is it will select just one location, one line. Let's say it is this line all the way down. Okay. In one of the lectures, we talked about how this direction is lateral direction and this is axial direction, right? So this one, of course, ultrasound is almost real time. B mode imaging, typically 100 frames per second. So M mode imaging is actually taken from a B mode image. So this is your B mode image. But M mode are these B mode images that you take, okay, over time. In seconds, okay? So if you have a frame rate, which is typical B mode, frame rate of 100 hertz, then each frame will be sampled at 0.01 seconds, right? Okay, so then basically this is your B mode frames, right? But I just told you that with M mode, you only look at one of these scan lines, okay? And what the doctor, the sonographer has the capability of is they can also move these scan lines at different locations in the image, okay? So what we're doing here, we have multiple frames going as a function of time and taking this scan line, okay? And for these, we'll call these now your M mode lines, right? So let me draw it to differentiate it from the rest. So this is your M mode lines now. You'll have a 3D data set, okay? And your ultrasound system is processing this in real time. So then you take each of this M mode line, it will get, put in a certain register, in your ultrasound system. And then another M1 line, 0.1 seconds later, right here, and then another one right here, okay? Now, these are just the grayscale pixels, okay? Each of these M mode line is one column of grayscale pixels. Okay, and so what it's now plotting, this will be as a function of time. Okay, so basically you can see movements of the heart because heart is a dynamic tissue. It will move, right? But because of the cardiac cycle, the heart will change its shape. Okay, so then you can see some of the pixels moving here, it'll go here, it'll go here, and you can see those gray pixels changing over time. Okay, changing in location over time. And so if you keep collecting, it will go as much time as you collect, and it will form a small video. It'll keep accumulating. Each of these MO lines will be accumulating as you're going through your B mode image. So how does this help, right? So basically, in echocardiography, it helps with looking at a location and the movement of one of the heart chambers, right? And you can see that it will, like, if this was 1 pixel in this part of the heart, then you can see it move and then relax, then move again, in sort of like a periodic manner, okay? It also can help you determine how long one cardiac cycle would be. If you don't have an ECG with your ultrasound system, then you can see how determine or estimate what the cardiac cycle would be. So basically, anytime this pixel right here reaches this location in the axial direction, again, this is axial going down here, and this is time, okay? Then it reaches the same axial location in another time like this. So now you can sort of measure this difference in the time. So I'll call that delta t. And from there, you can learn about the heart rate of a person. Heart rate, right? The rate at which the heart is pumping, relaxing, and diastole and systolic when it's contracting. So this is just one of the ways. And based on the amount also that the pixel has moved, that means you can also tell whether there is enough movement in the heart or strain in the heart that will say that it's within the healthy strain rate. Okay. If there's some damage in the tissue, there's some damage here, that damage can prevent the heart from contracting. And so the heart probably will remain stationary because it's not going to move anywhere. So this happens when a person has ischemic heart disease, which can eventually lead to a heart attack. So it's good to look at heart motion so you know that the heart is also pumping blood out into the rest of your body, which is important for you to for your daily living. So this is the main use of M mode imaging. And you can use it also for other applications, how muscles move. So you can use it for skeletal muscle imaging, especially in sports or rehabilitation. Okay, so anything that moves in the body, you can use motion imaging. Okay. So that's about M mode, and I think I'll just answer one more question. Okay. So let's see. If we have time, I'll get to the other one also. Let's look into okay, someone asked why the frequency used in echocardiography lower than transcutaneous ultrasound. Okay, so this is the question, why frequency used in echocardiography. So glad we already talked about echocardiography. is why frequency use is lower than transcutaneous. Okay, so first, we already know what echocardiography is. Now let's talk about what transcutaneous ultrasound is. So when you talk about transcutaneous, we talk about the imaging through the skin. Okay, so of course your skin has certain layers, subcutaneous layer and so forth. Then you get into your fat, then you get into muscle. So this is your skin layers, your fat, depending on which part of the body you are, and then muscle below it. Okay, and all the other internal visceral organs. We call it visceral organs. Okay, so if you can imagine, all right, what do I mean by all of these layers of the body? If you look at your stomach, right, you have your skin layer, and sometimes there's fat in there. Then there's your abdominal muscles, and then below or within inside your muscle is your stomach, your intestines, and so forth. So that's what I meant. So transcutaneous ultrasound usually refers to this layer. Okay. Usually uses higher frequencies, which is what this question implies. Echocardiography uses lower frequency. So echocardiography, you want the ultrasound to travel as far into your chest as possible so you can image your entire heart, right? So you can image all of this, all right? So the frequencies used for echocardiography, I'll just write it here, is 2 to 4 megahertz, all right? Transcutaneous ultrasound can go, even beyond 10 megahertz, okay? So then why frequency in echo is lower? Basically, we understand that there's a trade-off between your frequency of imaging, your ultrasound frequency, and the depth at which you can image. Basically, it's called depth of penetration, or I can say depth of imaging. Okay. So the higher the frequency, obviously, you get lower depth of imaging, lower depth. So for echocardiography, you need lower frequencies to be able to image deeper into the tissue. For transcutaneous ultrasound, since it's much superficial right here, your skin layers, fat layers, then you can go even higher frequency. Of course, the advantage of higher frequency is you have a better spatial resolution. And what this means for ultrasound is you can see even smaller structures, getting backscattered information from even smaller structures. Okay, which is for skin, it's a fairly thin structure, right? So if you want to image as much of the skin, you need higher frequencies, which works also because you don't have to image too far deep into the body, right? Skin is the outer covering. So this works out. If for echocardiography, you need to image, centimeters, more than 4-6 centimeters deep into the body. So you would need a frequency 2 to 4 megahertz. They can actually penetrate deep into the body. So then, for instance, so why does depth of penetration, why is there an inverse relationship, right? So basically, why does this happen? Okay. So it's well known that if you increase the frequency of ultrasound, you are also increasing the absorption of ultrasound into the tissue layers. So for instance, if I can give you, okay, the acoustic attenuation relationship through the tissue as a function of the frequency of ultrasound here, usually in megahertz. Okay, acoustic attenuation is usually in decibel per, in the body, it's per centimeter. All right. So then you have this type of relationship. Okay. Sometimes it can be even some power law. In some cases, it will lower frequencies, a linear relationship, linear increase. And then at higher frequencies, it can be a power law relationship. Okay, so it just depends on the range of frequencies that you are looking at. Okay, so let's say for echocardiography, this is 2 to 4 megahertz. All right, for transcutaneous, more than 10 megahertz. So let's say 10 megahertz falls somewhere here. So you can see that, okay, as you increase the frequency, you're losing a lot of signal, okay? And if you go deeper, so that's where this centimeters comes, then even more signal gets lost, okay? Manu, do you want to add anything?
No, ma'am, I think that answers the question.
Yes. Yeah, so yeah, for this case, I think it makes yeah, the increased frequency is only good for superficial tissues. You can get better spatial resolution. And at the same time, attenuation is that not that much based on these lower depths. Okay. All right. There's this one other question, but I think to port the image into my iPad would be challenging. So Manu, is there any other question?
No, ma'am, that's it from our end.
Okay, okay. So okay, let me try to draw what was in the slide that was being asked about. So basically, someone asked in terms of the correlation methods for shear wave imaging. Okay, so we're looking at shear wave, elastography. This was the slide where it was on, right? Ultrasound elastography. So maybe I'll name it ultrasound. Okay. Someone asked about the autocorrelation methods. So in that lecture, I talked about autocorrelation methods, which are used to basically monitor or track. Okay, I can also say compute, okay, displacements of tissues for elastography, right? We had talked about phase difference methods. So if this was your ultrasound signal, this is going in the axial direction. The phase-based methods looks into the how much this has displayed, okay, over a certain small range. Okay, so there could be a phase difference happening here. And that phase can be related to or proportional to the displacement. Okay, so these are the phase-based methods. Okay, so these are useful for smaller, relatively small, less than half a wavelength displacements. Okay, now you have what's called the spatial correlation method. Okay. And in this case, you're now looking at the envelope. All right. So basically, if you have your signal that looks something like this, axial signal, you would need to calculate the envelope, which we had described in an earlier slide. So this is the envelope. All right. And there'll be a shift in the signal, right? Because no shear wave is going through, or some motion, tissue motion is going through. So you would need to calculate another envelope for that. All right. And basically what is being used here is that you detect what this displacement is between the envelope peaks. So these displacements of envelope, you'll have to compute it. Okay. And this is called spatial method just because it's covering a large spatial range. It's mostly looking at the exact distance between the two. And then this kind of method is basically for relatively large displacements. Okay, so even more than half a wavelength displacements. And this is useful for when you're looking at large, like strain estimates of your tissue. So I hope this will clarify what's these two concepts. And then in that slide, we had said a combined method where you use both of these techniques to be able to cover the entire range of displacements estimates that can be observed in a tissue. Okay, so I hope this answers the question for that one. I think we're running out of time, but if the students have any questions, they can ask the questions through the discussion forums. We regularly check them and try to respond as soon as possible. All right, so we hope this is a good learning experience for everyone about ultrasound, and we'll see you soon. Okay. How about Manu? You have anything to add?
No, ma'am.
All right. Thanks. Okay. Bye, everyone.
Thank you, man.
Thank you.